Hello and welcome to another Practically Clojure session with me, John Stevenson. Thank you very much for joining today. Today we're going to do some 4Clojure exercises, and we're going to cover number 54 and 55, and if we've got time we'll do number 56. The interesting thing about these exercises are they have restricted functions. Those functions are probably the ones that will help us to solve the problem very easily, but it gives us a chance to dive into those functions and understand how they work a little bit better as well. So let's dive into the code, and let's go to number 54. So here we want to, it's asking us to write a function which returns a sequence of lists, and each list should be an item that's the size of the argument. So in here we're generating a sequence of numbers using the range function. So this is going to do a range of 9, and it's going to generate numbers like 0 to 8, because range, this 9 represents the last number to generate, but it doesn't generate that number itself. It's exclusive. And this number, this argument we're passing into our function, is going to be the size of these subsequences that we want to generate. So we need to write a function that takes two arguments, a number and a sequence. The sequence should be transformed into subsequences of the size of the number, and we need to make sure that we're not including a subsequence that's too small. So if there's not enough items left, then we need to drop those additional ones. So we can see when we look at this third test, we've got range of 8, and that's generating 0 to 7, so that's 8 numbers. But when we divide 8 by 3, that's not an even division, so we're going to have a couple of numbers left over. So we would have 6 and 7 by itself, and that's not a subsequence of size 3, so it's asking us not to return those at all. So that's basically the problem space. It's fairly simple, and it's a very simple thing to do in Clojure, unless you're not allowed to use partition, because partition makes it really simple, because that's basically the behavior of partition itself. So if we look at partition with the first test, give it a partition size of 3 and the sequence, and it generates a sequence with 3 partitions there. That's not a problem, and it even takes care of the edge case where if there's not enough numbers in the sequence so we want to partition, it will just drop those. So here we don't have the 6 and 7 left over because they don't make a partition of 3. And then, okay, so we could use partition all. If we do use partition all, which we're also not allowed to use, then it works exactly the same, except it does give us those last 2 numbers as well. So sometimes you do want the extra numbers. I've done challenges where I do need the whole kind of result sets, even if they're not a complete subsequence. But in this case we do need to drop them. So if we're allowed to use these functions, we'd use the partition rather than the partition all. Okay, let's see. Boom, boom, boom. So how are we going to solve this? Let's look at the classic loop recur. In this example, for this challenge, actually, loop recur isn't too bad. Actually, it's pretty straightforward. It's a low-level approach, but it's a fairly simple one. It's not as big as the challenge that we did last week, number 53, which had a very huge loop recur solution. So here we just, I'm using XS as a common Clojure abbreviation to refer to a sequence. So wherever you see XS, that means a sequence or some kind of collection in Clojure. Especially when you look at the Clojure documentation, you'll see XS and other things like that there. So I've got a function here that's going to take in the number, which is the size of the sequence we want to generate, and the sequence itself that we're going to process. And inside that we're going to have loop recur, so we're going to go and iterate round the sequence using loop recur. And we've created this local name that's going to point to a vector, and that vector is going to collect all our subsequences. So we're going to add all our subsequences here as we go around the loop, and we've got the sequence itself in there as dash sequence, and we're going to we're basically going to reduce the size of the sequence each time by the number of elements that we take, so it's going to get smaller as we go around the loop. And we did say in our algorithm that we've written here that we need to check to see if there are enough elements left, and we could do that with a very simple if function. So if the count of the sequence is smaller than the sequence size, then we want to stop processing the loop. If our subsequence size is 3 and there's only 2 elements left in the sequence, then we want to stop basically, and just return whatever the subsequences are. If we were past a sequence of only size 2 and our subsequence is supposed to be 3, then we just stop here. Any questions so far? So assuming that our sequence is bigger than the subsequences that we want to create, then we'll go through the recur, and essentially we're just going to create new values for subsequence and sequence. So we need to satisfy, when we call loop again, it's like calling a function. We need to pass it the arguments, the values for the names again. So we need a value for subsequences, so that's basically taking our first subsequence, which we can use the take function for. So take will take a specified number of elements, which is this subsequence size, from the sequence. So if we've got a sequence of 0 to 8, and our subsequence is 3, then we'll take 0, 1, 2, and so on and so on, and then we'll drop the same number of items from the sequence and pass it back to the loop, and go round and round and round until this condition is true, that there's fewer items in the sequence than the sequence we want to, the size of the sequence we want to create. So it's pretty straightforward in terms of loop recur, but we could probably go a little bit better as well. So yeah, here's just an example of what we're doing with the if logic. So basically saying if the count of 9 of range 9 is bigger than 3, there, well, if the count of 9 is less than 3, which is not, it's 9, then we'll continue because that's false. But if it's smaller, then this expression is true. Then if that's true, then we'll just stop and return what we've actually got in the subsequences collection that we're creating. So essentially what we're doing is we're going to create a subsequence, and then we're going to conj it into the empty list, and then we conj the next subsequence onto that, and the next subsequence onto that, and we get the right result. Simples. So let's test it just to make sure it's doing what it's supposed to do. So let's put the debugger on. So I'm just running the cider debugger, and now we can step through the values as we walk through the algorithm. So here are arguments. So our range 9 is generating 0 to 8, which is passed in via the function, and we're assigning that to the local name of sequence in the loop. So we haven't changed anything yet. That's going to be, the count of that is 9, so that's obviously bigger than the subsequence. So that's false. That condition, we don't have too few elements in there, so we have enough elements basically. So we are going to go around the loop again by calling recur. So subsequences starts off empty, but then we're going to take the number of the subsequence size from the sequence itself, and we get 1 2 0 1 2, and then so that gets added to, that's our first subsequence we've got, and then we have then we just drop those numbers from the sequence and pass it back. So now our sequence is smaller, it's only size 6, and the sequence is 3, so that's still bigger. So we'll go around the loop again and again and again and again and again. Boom, 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 and go round and round. So we're basically pulling it all the subsequences, and we drop the last, because we're dropping the last of those numbers there, we get the empty list back. We don't get nil, we get the empty list back because it's still a list, but just no values in that. It's a perfectly legal value, an empty list in Clojure, so we pass that back. We can run count on that as well. It's of size 0, so 0 is definitely less than 3, so that's true. So then we can return the all the values that are currently in the subsequence, and boom, and that's our result. There we go. So that works. If we didn't have the if statement, it would still work for the first two challenges because they are of equal size. It would just partition them. But if we didn't have the if statement, if we didn't have the check here, then it would fail the third test because it's an uneven number of 3's in 8 elements. So the if catches that and makes the makes the third test pass there as well. Okay, but can we do anything a little bit more interesting? We could probably do a recursive function, but that, again, I don't think that would be much different. We'd still be doing take and drop, and I don't think it would add too much more. Might make it a little bit smaller in terms of characters, but not really kind of using the abstractions we're looking for. There is group by. We're allowed to use group by, but it doesn't really help us kind of group it because it's grouping by, what would we group it by? Group it by count. Didn't really seem to work that well, so I didn't really think it was that useful for this challenge. We are doing a take and drop approach to this. So this is essentially what we're doing. We're actually kind of starting at the 0 and taking the first 3 elements, and then we're dropping those, and then doing the same thing for 3, 4, 5, and dropping those. So there's definitely like a start and end point we're trying to get to, and using take and drop to do that. So that's kind of working in our loop recur already. But that's like thinking about range itself, and range also has an optional argument where you can kind of set the step size for something. So if I'm going to generate, if I'm generating range 9, it's just going to generate 0 to 8. So I'm going to have my 9 numbers there. However, if I put a step value in there, then I'm only going to get 3 numbers because I'm going to step by 3 each time. So if I did a range of step, if I did range, and because we're using a third argument, we need to specify all the arguments. So we need to specify the start, which in this case I'm going to put 0, and if we do 9, which is the end point, and then the step. If we did a step of 1, we'd actually get the same values there. We'd get the same results as just doing range 9. If we do this with an odd number, if we did this with 2, we'd get all the even good numbers. And doing range 3, we're actually getting, we're getting 3 numbers here. In this case, we're actually getting the start points. So 0 and 3 and 6 are the actual start points of our of the subsequences we want to create. So that's 0. 3 is another start point, and 6 is another start point. So maybe we could actually use that in some way to be able to find the starting point of subsequences and then pull them out. So that's where I started to think. And then it started to feel like we wanted to kind of iterate. Because we're iterating around there, I thought of the list comprehension function called for. and so this is a really powerful way to help you kind of process lists in different ways. And so I thought that might be an interesting approach. And a classic example of using the for is so if you've got a lock with three, like combination lock with three tumblers, and each tumbler has a value of 0 to 9, and then you can just generate all the combinations of that lock there as well. So if you wanted to have a random combination generator, then you could use this to generate all the ones and just randomly choose one of these results as your lock. So this is just generating all the permutations, because each time it's going round, it's going round all the combinations. So it starts off with a lock of with everything on 0, and then it just moves one of the tumblers to the end, which is, so we go from 000 to 009, and then we put that back to 0, and then we start going through the second tumbler, and so on and so on. So it's just basically generating every single permutation. So how can we apply this to 4Clojure? Let's see. Yes, so we've got here we've got our function again, just the same. So instead of doing a loop recur, we're going to use the for function, and it's we're defining a name which is going to be the collection of start points, and we're basically going to generate those. So we've got a range here from 0 to how big the sequence size is. So this is going to be, in our first example, it's going to be 9. So we've got a range of 0 to 9, and we want a step of 3. So that would generate our start points there. Oh, sorry, wrong one. Let's do that. There we go. And you can see that yeah, so basically we are just for an example, we're just putting string around the start point, and you can see it's returning something for each of those start points. So we're basically iterating around just the start points. So that's kind of, rather than kind of taking and dropping, we're just going straight to, we're just basically creating a structure that kind of starts us in the right place in our sequence each time. And then we can use take and drop, because I think that's probably, I don't think there's anything more simpler than just using take and drop, except this time we're doing it with respect to the start points each time. And so if we evaluate this, we get our results, because what we're doing is we've got our start points, which is 0, 3 and 6, and we're going to basically drop from the start point. So in the first time round, so for the first 0 element, we're just going to drop 0 elements and then just take the first 3, and then the next time round we're going to drop the first 3 elements and then just take the next 3, and then the last time round we'll drop the elements and take the first 6. Let's see if this will, can we debug this? So let's have a look. Yeah, so we've got a count of 9, subsequence of 3, range of 3. So we want to take 3, but first we're all going to drop the results. So if we drop 0 results, 0 elements from the sequence, we've still got that sequence. So we get the first subsequence we wanted, and then our drop is now 3. So we get, so we can take from that result, so which is 3, 4, 5, and then the third time round the for loop, our start point is now 6, because that's the next in the start point list, and then so we take 6 from that, and we left with 3 there as well. So that's kind of an even nicer, I think, abstraction over the loop recur, and it's doing the same thing. One thing we have to do is, so this is doing I guess this is doing the equivalent of partition all by itself, and we can but we need to fix the fact that we don't want the extra numbers when we do the third test. So when we do this, we got the 6 and 7 here, and we don't actually want to return that because it's not a complete subsequence. We don't have the 3 values in this last subsequence. So how can we do that? Well, we can put something in when we're doing the calculations about how many times we want to get the subsequence. So let's do that. So we're adding a let statement in here to understand how many complete subsequences there are going to be. So we're kind of doing an upfront calculation to say, okay, well, if we process all of the sequence into subsequences, how many of those are actually going to be complete? How many of those are going to be full? So if we're dividing in this example, we've got a sequence of 9, and we divide 3 by 9, we're going to get 3. So that's how many subsequences we want. Whereas when we divide a range of 8, which is size 8, 8 elements in there, by 3, 3 goes into 8 2 complete times with some remainder. And so we can use this quotient function to actually give us just the whole number. So this will give us the answer of 2, because 3 will go into 8 2 times, and there will be some remainder. And there is also if you just wanted the remainder, there's also a rem function. So this would just give us the remainder, which is also 2. So if we did another number, 10, so this is going to give us a remainder of 1. So we can use quote to kind of see how many times the subsequence goes completely into the size of our collection, the size of our sequence, and that will be the kind of control. So rather than kind of stopping before we get to the end, we'll just generate all of the sequences and then just take the sequences that we actually want, because we know how many there are going to be that are complete. So this is what we're doing here. So we're adding this quote into here, which just takes the size of the sequence and divides it essentially by the subsequence size, but just returns the whole number, the complete number of times that the subsequence will go into count. And then we can use that as the thing that controls how many start points we generate. So in this example, if we use the 3 and the 8, we're only going to take we're only going to have a start point of 0 and 3. We're not going to have a start point of 6 because it's not going to generate a complete subsequence. Let's see if will the debugger show that? It might do. So that's a range of 8, and we're going to. So we've got a size of 8 for that sequence, and we divide it by 3, and that's going to give us 2 because we got 6, and then we got 2 remainder. So that's the size of the take we want to get. So we've wrapped this range, this kind of range of start points with a take to only take the ones that are going to give us a complete subsequence. So let's see, so we've got 8 subsequence size 3, so that's going to generate all the start points. However, then we're like chopping those down, we're trimming that's the start points down by taking just the number that we know are going to give us complete subsequences. So that's our start point, and then the rest of it is just the same. So we just go through the rest of it and take the first sequence, take the second sequence as well, and that's it. And we stop because there's only 2 start points in this for loop, so we don't go round again. We can just ignore the remaining values and pass that back, and we get the results. So although it doesn't look any smaller than the loop recur, I don't think. Yeah, if you take out all the comments, there's a little bit of size difference, but it's a little bit shorter, and it's I think it's a lot nicer in terms of abstraction there as well. Cool. Any questions on that? Some people seem to be afraid of 4. They don't think it's a very functional approach to writing Clojure code, but it's I mean, it is a macro, so there are a few interesting side effects, but it's a very powerful abstraction in Clojure, and it's definitely a really useful function to be comfortable with. You might not be able to like compose certain things using a 4. That's probably the main limitation. But if you're doing some list comprehension, if you're just processing a list, it is a very nice, clean way to do that. And there are other features of 4 that you can include as well, because it's a macro. I'll have to do a particular episode on that at some point. Okay, well that's I didn't find any other examples on 4Clojure that were of interest really, so I'm going to stick with mine. Back to the web page, and which one did I put in here? So yeah, so that's what I've got in there, and just to show you it's all working, I'm just going to run it. Yeah, we get all green. Any questions on that? No? Right, let's move on to the next one. So we've got to count occurrences, and again we've got another restriction here of frequencies, so we can't use frequencies. Frequencies is a really nice function. I've used that in the example where I do most common words, and I'll put a link to that in the show notes. So what are we doing here? So we need to write a function which returns a map containing the number of occurrences of each distinct item in the sequence. If we think about what we were discussing in the challenge we've just done, we did kind of briefly explore a function that might actually help us here. So let's go, before we get carried away, let's go to the file, let's save that, and let's load in number 55. There we go. So we need to define a function. We can do that. Hopefully we're happy defining a function now, and it's taking an argument that's a sequence, and it's going to return a map, a hash map. And the keys of the map are the unique numbers. So here we've got the key. So key can be kind of pretty much any legal value in Clojure. You can even have a function as a key, because it returns a value. And so the keys here are the numbers that we find in this collection, in this vector. And so there's 1, there's 2, and there's 3. Those are the unique numbers that are in this particular collection. And we've got number 1 appears 4 times, number 2 appears 2, and 3 appears once. So that's what we're building up, and this is the same, and this is pretty much the same as well, except the only difference here, I mean, we're using keywords here, which are just like symbols that point to themselves. That's pretty easy to deal with. And then we've got elements in this sequence are actually vectors. But it doesn't really matter, because we could just use that. But we can see that 1 and 3 and 1 and 3, that's the same value, because 2 vectors that contain the same thing are the same value. So then we get 2 of those in there. So that may or may not cause an issue. Let's have a look as we go through. So that's it basically. So the keys are the values, and so the keys are the elements of the original sequence that are unique or distinct, and the value for each of those is how often they occur. So we did mention group by in the previous one, but it didn't really help. But if we group by identity, so it basically groups by the thing it is. So what kind of thing is it? So we've got to group identity of 1 is 1, identity of 2 is 2. But group by is actually creating a map for us already. So it's kind of doing most of the work for us. And it's quite nice that we can just dive in there. I don't think we need to kind of go into a loop recur in there if you want, but feel free to go in and explore if you wish. But the one thing it's not doing is it's not giving us a count. So this is probably where the tricky bit is, and where frequencies does its magic. So how do we turn this this value here into the count of this value? So this value of 1 is a vector, but what we actually want is the size of that vector, and that would give us then the how many times that number 1 appeared in the original sequence. So we're very close, temptingly, desperately close, but now we need to try and figure out how to actually replace each of these values in the map with a slightly different value. So we can use a reducing function to help do that as well, and basically create a new map that has the keys as they were, but as we go through the keys, then we're replacing the values of each key with the count of those vectors, and then that will give us a new map, which should be the shape of the map that we're looking for. So I've written a simple kind of reduce. It's going to take a function definition that I've written, and it's going to work on it's going to create put things into a new map, and from the results of grouping by identity of the original sequence. So we're going to reduce. So this function is going to take an empty sequence. So in this case, it's taking an empty map, and we're going to do we're going to go over the key value pairs. So we're doing a bit of destructuring here. So in the map, we can treat a map as an associative structure. So basically, a map has got a key value pair in here. So let's see. So let's just do that for us. So map's got a key and a value, and it's got multiple of those. So when we reduce over it, we're going to grab basically the first two elements of the map, which make up the key value pair. So this is what this destructuring, this is what these square brackets in here is doing. It's going to pull out the key and value as we iterate over the map, and then we're going to associate into the new map that we're creating. We're going to take the key as it is, and then we're just going to give the value to the count function, and the result of that will then go into the new map that we're creating as the new value. So if we do that, then we get the right result. So we're grouping by identity to create the map, but with the wrong shape of the values, and then we're using this reduce function to go over that to basically turn the vectors into a count, the result of the count. Oh yeah, and this is just how I wrote it for the 4Clojure. So yeah, basically putting this into a function. I guess you could have put, you could have put in the short form of that as well if you wanted to, and just save on your golf scores. So if we look at this test for this, so we've got our function, it's going to take our sequence, then we're going to reduce by it, and we've got our group, we're applying group by identity to the argument before we reduce over it. So we've given it here one of the tests. So let's just do that, and that's giving us the right results. So if we group by identity, you can see that it's creating the map with the numbers, but then vectors of how often they occur. And we've got we want to build up a new map from this empty map here, so our key at first is 1. So we get the first key, and then that's got a vector of 4 elements. So we put that into the map, and then we go around to the next one, and next key is 2, and that's got a count of 2, and so on. And then the next key has got 3, and then that's got a count of 1, sorry. And that's the result. So we put that. So our reduce combines all those updates into a single map, and we return a result that way. Simple. So there is a nice another approach we can use. So this is pretty nice. Just using reduce is really nice, but there's a slight abstraction we can create on top of that, which is the into function. And this is, I don't think there's a huge amount of difference in here, but we're basically, I think it's a little bit easier to read overall. Here we've got, so we're going to put something into a map, and it's essentially using like it's kind of like a reduce conj under the covers of into. So basically, into is going to reduce all the values that we're going to get by mapping a function over the group by identity. And it's going to collect all those values and put them into this map. And you can also use into with vectors and other data structures as well. So let's see. So this is kind of working pretty much the same. So we go into the map. So the map is, instead of using reduce, we're using map to map a function over each of the key value pairs. So here we're still doing some destructuring of the results of group by, and we're returning a map with the key, and the value is the count of v. So that hasn't changed either. So our function is pretty much the same, except we don't need to specify like the empty reducing map, because we're going to gather those into that map using the into. So this is going to generate like a number of maps, and then we're going to pull that into, we're going to reduce conj that into a single map form. So let's see. So we've got our original sequence, and then we're going to group by identity, so it turns into our almost there map, and then we're going to count the values of each of the values in the map, and that's going to then be fed back into, so you can see that we've got a sequence of maps, and then we're going to reduce conj into a single map, which is what the into is doing for us, and then we can just return that as a result. So that's a really nice approach to that. I think I do slightly prefer that. I think it's a little bit easier to read. There's a few less moving, it feels like there's a few less moving pieces in there than compared to the reduce. And it's fairly upfront about what it's doing. It's basically putting the results of this function, this map expression. It's going to put the results of that into a map, and then you can pick into the what's the actual map doing, and so on. So I think it's a slightly nicer abstraction, I think. and nobody's disagreeing with me, so yay, there we go. So I think those are the answers I came up with. I think that was the one I did. Yes. Let me just see. Is that the one I put into 4Clojure? Tab. So the count currencies. Oh yes, yes. I used that into. Just double check. And again, I don't think there were any other solutions. This next one is to. I don't think I've finished this one actually. So I'm going to. Oops. I have solved it, but I haven't kind of described how I'm going to solve it. So what I'm going to do is just leave this as a slightly shorter episode, and I'll do this next week. Thank you very much for joining me, and my name is John Stevenson, and this has been Practical Clojure. If you have any comments, please leave them using the details on the website. Talk to me via Slack, via the Clojure Slack channel, on the Practicalli channel, or by Twitter as well. And feel free to. Sorry, I'm not asking any questions. It's okay. You don't have to ask questions. That's fine. As long as it all makes sense, you don't have to ask questions. If it doesn't make sense, I'll be worried if you didn't ask questions. But feel free to reach out, and if you've got any suggestions about things you want to do, then please let me know. Hopefully I will get round to eventually building this website, which has our list of all the playlists on there, but it's still the best source of finding all the playlists is by going to the YouTube channel and looking at all the we've got 34 of these now. Actually there's probably a few more because there's a few incidental ones as well, and I will get around to eventually building this page and making it look nicer. Yeah, I might not use Bootstrap. There we go. Okay, thank you very much for joining me, and I will see you next week. Thanks. Bye bye.